Cloud. Please.
So, thank you, Jan, for the introduction. Thanks for the invitation. And very nice to meet you all. Thanks for coming to the talk. So, as Jan said, I'll be talking about the multigap topological insulators, which are the main focus and the unifying theme of my PhD. Because, okay, first of all, I'll be talking about the phases of matter, but that are beyond the conventional classification of single gap topologies, right? You can have an insulator with just a single gap where you put the Fermi level. I'll be talking about the phases that can have multiple gaps. So I'll be able to partition bands, which I will discuss between multiple gaps. And I'll try to induce new topological invariants in that way. And then you'll see how we can also connect some physical manifestations. Okay, so before we move on to the particular multigap topological insulators, but I had the pleasure to also describe during my PhD, I'll give a basic overview of how we define the multigap topologies. And that is essentially based on this physical review paper by Adrian Hopf, Tomasz Wojciech, and Robert Jan Slager, my advisor. And well, to define, of course, we need to begin with our system. Okay, so what's our system? So we consider three fermions on the lattice. So let's say I have a periodic medium of some lattice with where my three fermions will be able to hop. We'll experience some lattice potential. And we will consider physical orbitals on the lattice. We will use lattice vectors R, and for orbital positions, we will also use displacements from the centers of the unit cell, and we will do completely non-interactive physics. So we will consider three fermions, and as such, any single particle state we can basically create by putting an electron at the orbital mu. We can call them like A, B, C. At the position as R, on a vacuum state. And that will be our physical orbital. I will denote as W, mu, plus R. So our Hamiltonian, which drives all of the dynamics of the system, we can write down in terms of this basis. Sum over all of the possible hoppings and on-site terms. We assume a translational symmetry, so we can hop between different flavors of orbital, right? In one unit cell, for example, from orbital A to an orbital B in another unit cell. Also, given the translational symmetry, we can rewrite all of this in momentum space. Momentum of the crystal momentum, given we are under periodic boundary conditions, to be a good quantum number. For the rest of the talk, we will not address any systems with disorder where momentum is no longer a quantum number. To write it in terms of momentum space basis, we will introduce Bloch orbitals. Basically, just by Fourier transforming from our Lie space physical orbital basis. So let me just very quickly. Okay. And on changing the basis, our translation isometric Hamiltonian can be written in terms of the Bloch orbitals as following.
Okay.
Where this is our block Hamiltonian. So-called block Hamiltonian. Yeah, yes, please.
So what was the? You got the Hamiltonian using the block openings as a base.
Yes.
So why was it necessary for you to write down the first one?
It was just, I would say, condensed motivation of thinking in these spaces in terms of the physical orbitals as given by chemistry and just hoping.
So logically, you could have started there.
Sorry?
Logically, you could have started.
Yeah, I could have started from here. In principle, yes, but from, I would say, more chemistry-driven point of view, I would think about some s orbitals, p orbitals between which I can hope with different amplitudes, which define the matrix elements of this.
I don't know the subject very well, so I'm just interrupting you. So.
No. Okay, so yeah, conceptually I could have started just here. Okay, that has all of the information about dynamics of my electrons too under translational symmetries, and moreover, it will encode all of the topology that we'll be interested in. Okay, so the block Hamiltonian defines an eigenvalue problem, which is basically a Schrödinger equation. The eigenvalue problem will give us the block bands. Also, the energies of the eigenstates. Okay, so that's our block state, which I will also show you. Okay. So essentially, if I know this vector for every single momentum k, I know all of the flavors of my energy eigenstates in terms of the basis of orbital ABC, and also the twists intuitively of these vectors will be encoding all of the topological features. So more formally, these vectors we will use to define a block bundle. For the rest of the talk, I'll be interested in the spacetime inversion symmetric systems. So the block Hamiltonian that I'll be interested in will actually be real. Okay, so essentially from the spacetime inversion, I'll get the complex quantification.
So your wave function are always real defined. Okay?
Exactly. So given the reality
yeah.
condition from the spacetime inversion symmetry, my eigenvectors would be real. So these are real tuples, and the dimension is given by the number of physical orbitals that you have. Okay? So the geometric picture is that we essentially have the Brillouin zone in which all of the momenta here live, given transitional symmetries will also be periodic. So the set of all of the k's we're essentially on the d-dimensional torus, okay? And then over this d-dimensional torus, for any k point, we have a local vector space that is spanned by the eigenvectors, which can be also taken orthogonal. Okay, satisfying the Hermitian eigenvalue problem. Okay, so this is a local space Vk, and Vk is basically a span given by all of these eigenvectors, which I will label with the band index. Okay, so given at which sector of a Brillouin zone I look, I'll have different bands. In principle, we will define the multigap condition in a second based on the separation of the energies that you have in the Schrödinger equation. Okay.
What about degeneracies?
We will also include them. Okay, so then if we have, but we'll also change the gauge structure once we have the degeneracies, because then we will be of course allowed to do larger gauge transformations because of the degeneracy, which will actually change the topology later. Okay, so we are allowed to have pairs of the mass. Actually, the most interesting topological charts will be related to having also band degeneracies, as we will show. But we
dimension of VK finite.
Sorry.
Is the dimension of VK finite?
Yes. So for our purposes, we are assuming that n is finite. Okay. So we essentially have we have a vector bundle with finite spaces here, right? And therefore also to fall beyond the classification of K theory, because K theory in principle would consider the stable equivalence limit where you have infinite possible number of n, right? We can always go to higher, and within K theory on adding more higher conduction bands up to basically ionization energy of our.
So at a given moment you fix a top limit on n.
Sorry?
You fix a limit on n.
Yes. So we're doing finite band partitionings. So let me. Okay, so let me just formally define this block bundle. So to basically a union for all of the momenta in the Riemann zone of funds. And we can think of that as essentially a total space, and of the Riemann zone as a base space, on which you have a projection. Okay. Our fiber is associated with the vectors that live locally. Yeah. Okay, so.
Sorry, may I ask what happens if you break PT symmetry?
So that's a very important thing. If you break PT symmetry, this will no longer be a real bundle. So then we can have an arbitrary CN. Okay. Got me. Okay, so we have finite n, and the multigap condition essentially imposed decided by partitioning of the energies. For example, we can have some degenerate bands, E2, E3, E2, n. And you require that for all cases in the Riemann zone, we'll have multiple gaps, right? So we have strong inequalities between some parts, of course, for 2 and 3, they can be equal. So we can essentially divide into some sub-bundles, okay, in which some interesting topology will be possibly seen, right? So to essentially get a sub-bundle, we can do here a finite constraint. And for a general one with multiple gaps, I can just divide my n bands in P1, P2, P3.
So maybe I can translate. I mean, your Riemann zone is basically a base manifold.
Yes.
You are building the gauge theory for each subsect of your bands. For your band, you build your gauge theory, given the base manifold is the torus.
Yes. Okay, so let's take all of these partitionings here. Sub-bundles. So, okay. So I can write run up to pk. And each sub-bundle, right, will be essentially some union of the finite frames, as Jan suggested, which should be spanned by okay, that's for P1. So number of bands that we have. Within the subframe, right? So we have a total frame of all of the eigenvectors, vectors, and then we can finitely partition that, and in particular we associate it with non-triviality of the subbundles, and we will be able to associate topological charges with these finite partitions, right? So what happens in the case of a single gap partitioning, where we just have one subbundle that is the valence, only one subbundle that is a conduction one. We can of course add more and more states within the stable limit, and with a single gap, we can actually classify it within K theory, but in that case, we'll be beyond the notion of stable equivalence. We'll be no longer talking about infinite bundles, we'll be talking about the finite partitions. And see what new charges can emerge out of these PT symmetric conditions. Okay, so now the question is, of course, how do we classify it if we cannot use K theory? We will use homotopy classification. So what we'll be doing is essentially we'll consider a flattened limit in all of the subbundles here. So we will send our Bloch Hamiltonian be essentially a diagonal matrix within all of these subbundles. So let's say if we have like from Pi to K, right, I can start from this K, wherever I put the energy zero, here's completely arbitrary. We're interested in what the eigenvectors are doing from the topological perspective and how it will translate also into physical observables later. So we can basically okay, so that's of dimension K up to say okay, so we just artificially can set the energy to be K for the K subbundle. So is the question?
Yeah, sorry, what does it say before classifications there?
Sorry?
What's the word before classification?
Homotopy, because we are connected to non-trivial homotopy. Okay, so we are working this flattened limit, which is basically, well, flattening for the spectral decomposition of this matrix, right? Because the H of K, I can write in terms of the spectral decomposition of K, and the diagonal precisely all these energies, P1, okay, where Rk is basically a matrix of these eigenvectors for every single K. All of the topology of the twist of our eigenstates will be sitting here. This we consider the flattened limit. And then what we'll be trying to do is to define a classifying space for any band partitioning that we can consider in the flattened limit. Right? So, and there are two things to it. So, in principle, we can consider the classification for these matrices on the direct mapping from a d-dimensional torus, but we'll be considering mostly strong invariants today, which we'll be able to classify with the mappings from the d-dimensional sphere. And this will make life much easier because we know the homotopy groups on mappings from the spheres. In principle, if we knew the torus homotopy groups, we could also do the classification directly here, but the computation of these groups is much more difficult, right? So if we look at the the homotopy group of our classifying space given the partitioning, then we will know what type of invariance we can induce in particular subbundles. Okay, but first of all, okay, the general question is, what are the classifying spaces for these flattened limits? So for that, we need to address the following things. So in general, the RK, given the n bands, this can be any O of n matrix, right? But we also have the gauge structure, right, that includes the degeneracies. So in principle, we can do orthogonal rotation between subbundles. So we need to take a quotient with respect to you see all of the partitions here. And that means that our classifying spaces will be real Bragg manifolds. Why real? That's because we are considering the spacetime measure symmetric systems. And basically taking the quotient and corresponding to the general matrices R with respect to all of the gauge freedom that we have in all of the right. Of course, the sum from P for all of the sum is separated by the gaps. This sums to n. If we, for example, get a single gap to begin with under this finite partitioning, actually we would have the Riemannians as the classifying spaces. So there'll be just one P for the valence subbundle and above the single gap, the rest, which is n minus p. And we'll just have O n quotient by OP plus n. So you're basically interested in the homotopy groups of these Riemannian manifolds, which are the classifying spaces for our Hamiltonians, having included also the gauge. Okay, but again, the key players can be actually here in the flag manifolds, where we say, for example, take 5 bands and introduce a gap between each of them, and indeed we'll be able to actually get some new invariants that are completely missed by the single gap.
You are flattening also to simplify, because you don't care about the kinematics of the particle, you care about the topology.
Exactly, only what happens in the winding of the.
Because each state is like a quasi-particle with a mass, the gap is a mass. So you have different masses of particle with some dispersion.
Yeah.
But because you don't care about the geometry, the dispersion, you can flatten them. So and you classify only the topological feature of this quasi-particle, right? In that sense, to
exactly. And we also see that actually if you close some gaps, you can trivialize particular invariants, right? And of course, the interesting thing will be that, well, given the presence of multiple gaps, actually we'll be able to trace these invariants with optics, right? Because if you, for example, do nonlinear optical processes, then you can have virtual transitions across multiple gaps, right? So you have the nice physical picture of how to pin them. Okay, so a few examples for those, because I mean that was more of an abstract point, but what kind of invariants can we get out of that? Is this slide?
Sorry, what group is in the bottom part of that quotient there? What group is that at the bottom?
So that's O of P cross O n minus P, right? Because this is just the two band, so the single gap, right? It'd be interesting the. By the way, we can also consider the oriented Riemannians and oriented flag manifolds, which I will denote with plus. It basically amounts to sending O to SO, right? So in that case, we are interested in the oriented subframes. And actually, the orientability might change the structure of the invariance. So what happens in real space is basically that if we have an eigenstate and we change the momentum of the eigenstate, the orbital flavor in like this basis A, B, C, D, that I labeled with mu, right? This will change as a function of k, which basically corresponds to what would happen in terms of the change of the vectors we are trying to move around a given k point, right? So that's the intuition. Okay, but in any case, so that's the homotopy classification, and let's discuss particular cases. Okay, so we can, for example, start with one dimension, and then let's say let's say that as a simplest case with two gaps, we will take a three flag manifold with 1, 1, 1. We'll look at the first homotopy group, so maps from the circle, and that's already quite interesting because it turns out to be the quaternion. Actually, if we have 4 bands with 3 gaps in between in one dimension, this is essentially O4 quotient by O1 times, so this would be, well, Z2. And that turns out to be actually split by quaternion algebra. In D equals 2, looking at pi 2, right? So we have a 2 torus, 2 sphere, and then our classifying space. And for pi 2, actually, this turns out to be trivial, but if you keep the finite band partitioning when you have 2 bands and then 1 band here that are isolated, we can essentially get Riemannian to 3. That is also real, as I said, we are in symmetry classification. Actually, if I look at the oriented case, this turns out to be essentially a 2 sphere. And then this would be a Z. It's like if it wasn't oriented, so if I had just the 2, 3, I would have had RP2 instead. In terms of the second homotopy group, this will actually still get the Z classification, but we also have the freedom in terms of orientability for the pi 1, so we can have Z2 classification.
In RP, you don't have orientability. You don't have orientability. RP2, sorry.
Okay, so that actually is a classification of real oriented vector bundles, and this turns out to coincide with the Euler class of a reoriented subbundle here, and that we would be actually able to calculate from the connection on this bundle from the homological perspective. Okay, so what do we have more? So for example, we can also look at the Riemannian or so that would be actually something to 2 spheres, so then we get that plus Z classification, and to be a pair of Euler indices. In 3 dimensions, it's actually something that I studied the most during my PhD. We can have pi 3 of the same spaces, right? Then from pi 3 of this Riemannian, we essentially get the Hopf vibration homotopy group. So we're talking about the maps from S3 to S2, right? And these are classified in terms of the Z index, which is the Hopf index, the Hopf vibration. So if this is Riemannian 3. We can also actually take the flag manifold as set these Multigap limit, right? So if I have flag 1, 1, 1, you can get again a single Z index. When we have flag manifolds with gaps, and let's say I take an oriented one, I will actually have just SO4, right? So as I said there, we can replace O with SO. Now SO4, we think of as two copies of free spheres. So I have S3 plus S3 quotient by Z2, and the homotopy of this will be Z2 is actually not changing anything for the third one, so it's by 3S3, S3, which is a pair of winding numbers on the free spheres. Okay, so this is again Z squared, and these indices I will call WL and WR. This index I will just call W. This index I will just call H. Right, for Hopf. Okay. We also actually did the case when we have Riemannian 1, 4, and then this turns out to be S3. So again, we can have 1 by 3 of S3, which would be exact index. Right. So that was the bad invariant, which, well, okay, I show how to get it in terms of the classification. Now, of course, we will need to construct it out of the vectors, right? And that's where cohomology theory will help us.
You're topologically classifying to be the space of flavors in a more particle physics friendly jargon. So you are just studying the fiber bands that are the internal space, no? And then you get the topological classification of this internal space. It's not the topology of the torus. It is a topology of
the entire
space
band.
attached that is flavor space in a particle or high physics sense.
So I got a bit lost in the nomenclature. So
Yeah.
still call this the homotopy classification, or is that now like KT classification?
Oh no, that's the homotopy classification for the multigap basis, right? Exactly. If I was doing the stable classification of a single gap and as many bands as I wish, right, with n being sent to infinity, principle that one could do with the K groups and the K theory. But here the point is that once I have the finite band partitioning, I cannot work in the stable convenient limit of K theory, and I can still get new invariants out of these subbundles, and that's really nice because we will actually be able to show that as we close the gaps, out of like many gaps, we can trivialize some of these indices, right? The entire point for the K-theory classification is that if I add some trivial subbundle, right, but keep the gap here, I will not trivialize the index. Unless I actually close the gap itself, right? So here we actually have topology that is only stable as long as we keep the finite band partitioning and multiple gap condition.
But also, for instance, the Euler that you get, it's not the Euler or the torus.
No.
It would be zero otherwise, right?
Yeah, it's of the two sphere.
In the sphere that is the internal space, like a tangent band or like thing, so it's part of the
exactly. So
vibration.
that's why it can be like this. Okay, so let's get it out of the. So for that we will define the connection on our bundle. So we have essentially A and N, which I will conventionally find the product. For I component, I will stick that Pi, then K. Okay.
So you're building the your gauge theory now.
Yeah. So I'm putting the connection on my bundle. Okay. So I'm putting a connection. Then actually we'll be able to also put the geometry by defining an inner product. So you also equip it with the Riemannian structure. Okay. For now, we just put the connection and we like get these homotopy invariants out of it. Okay. So that's our non-Abelian very connection.
It's like a non-Abelian Yang-Mills theory momentum space. It's basically this. We're building Yang-Mills theory.
Right, so for Euler, as John Domenico mentioned, right, we can define also an Euler connection. When we take Fabian of some subbundle, or actually of the non-Abelian very connection matrix defined for a subbundle. Okay, so I'll take a Fabian, right? For some subbundles, we can, for example, take to be just two bands. So I'll take some P that is running through two bands for the 1 and 2, right? And then we have 1, 4 defined twice, right? Because I have a matrix for, of course, every index I. Okay. And of course, I'll be also later able to define a curvature with that two form. And my future derivatives. So that actually had been done in a also my collaborator Adrian, nature physics paper. And then okay, here, if we take just a bundle of two bands, as I was doing here, we can essentially reduce this Pfaffian to just make its elements A and n plus 1 for some small n. So element-wise, this will form the following form. Notice that I'm taking different ones and n plus 1. Okay. J. And the Euler invariant can realize in terms of non-trivial in terms of elements of non-trivial elements of the second cohomology over our original two torus integers. Okay, so I'll do an integral over our base manifold, which is two torus. And that indeed will take values in integers, but will coincide with the integer there. Come from the round homology, second one over our two torus. Okay, so I have a reorientable subbundle with these bands and then plus 1. This is completely real, by the way, the connection, of course, by definition. And again, I'm just differentiating real vectors and sandwiching them with the real vectors. And then we can get a Z quantized index out of that. But we'll have some physical manifestations. Actually, we can promote it also to the integration over a patch rather than.
What are you doing here? Why are you covering that chi?
Because it coincides with the Euler class of this subbundle.
Yeah, but wouldn't another symbol be better, considering you have torus?
Okay. So what is true is that I mapped it implicitly to S2. Right, so it coincides with the Euler characteristic, right, for the two sphere, right? Even though we can think about this two form as being defined in terms of the eigenvectors on the torus.
Okay? Yeah, pull it back.
Yeah, exactly. So I can do it. It's true, right? But that's true as in the construction of the classification, we have the two sphere sitting there, and actually we can think about the Euler class in terms of tangent bundle of S2, right, which was our classifying space. And the normal bundle. So if I have these two bands, I can think of them as spanning the tangent bundle. For the normal one, for the vector 3, right, I will have them living in the normal bundle, and in principle, we have a Skyrmian-like texture in the third band whenever this tangent bundle is singular. Okay, so actually by Haribo theorem, this will also show that if you try to, use this tangent bundle over this here, you will get necessarily some band degeneracies, right? So you cannot take a globally smooth vector bundle here. That will actually, that's essentially a proof of why these two bands with the Euler charge will also have the band degeneracies, right? So we cannot make globally smooth PS2 here to get the bands without and singular. So that's pointary Hopf theorem in disguise. In that case, right? As I said, that's essentially a result formally is it to Haribo theorem. Okay, so that was the case of the invariant. We can also look around these degeneracies. So I have somewhere over the K-space a patch in the Brillouin zone. I can think about the vorticity of my Euler connection. And even on the patch as an abstraction to Stokes' theorem, I can think of the Euler class as integral over the curvature within the patch, from which I will subtract also the boundary term. Of course, the Brillouin zone is compacted, there's no boundary. So in that case, we have no boundary term. But in principle, we can promote this invariant over the entire Brillouin zone to also a patch invariant in our Bloch bundle. And actually, we will later discuss like how the patch invariant itself can be actually physically manifest. So the physical reason to that is, but again, if we think about having these bands with some degeneracy, you can actually change the occupation between them. We can pick out the connection, but from optical responses. But there we will get slightly later. So the physical manifestation of even patch Euler class can be in principle retrieved. Okay, so that was the Euler class. Let's talk about the other invariants now. So for example, the winding index here of this like manifold 111, we can get cohomologically from integrating now in 3D a wedge of connection with the curvature. And actually same with the Hopf index, mathematically have equivalent form. We can actually where we can define a one form based on the quaternion construction. Again, quaternion construction is related to the Hopf operation. I will explain how in a second. So I'll take the new part of I'll just define this quaternion in a second. Okay. So quaternions. Take on the normalized ones. So the way I will get the quaternions is I take the third band here, so call it U3. I can compose it in terms of the I have just three bands in a vector with three elements. Vector and the z vector, where the z vector the coefficients in the quaternions. Okay. And right, so the way we think about this is that I have my Hamiltonian, I have my eigenstates. The eigenstate 3 can be decomposed in terms of the z vector and the poly vector. The z vector has these real and imaginary coefficients here. Then, if I put it into the quaternion, I have a one form, and the one form for the Whitehead formula is actually equivalent to the Hopf index, right? And why could I do the quaternions here? Well, fundamentally, the structure is hiding because when I think about the Hopf vibration, right, which is mapping S3 to S2, we know that these S2. So we have this SU2 structure hidden in our block bundle. Okay,
It's
so
off, no?
sir,
Because it's off.
sir.
Because it's an off structure, no? That's why. But this is also a Chern-Simons at the end, no?
Yes, yes, it's
Yeah,
just Simons, but,
just,
but of course we can formally also get it from the Whitehead formula.
Yeah.
From the quaternion solution. Okay, that's true. It is Chern-Simons under the constraint of the reality.
Oh, there
So we have
it's
bits,
like a sort of gravitational Chern-Simons here. The Abelian limit.
Okay, I don't know what I believe. Okay, cool. So we have the syntax. Now we can actually also do it for the pair of these I call it isoclinic winding pieces, which are actually introducing this paper. Here,
How do you remember those numbers?
sorry,
How do you
memorize
remember?
them. And this we have because Polish actually the next issue. So, but this is what I was memorizing in the moment, of course. 2024. Okay. So basically, what we did, right, is to introduce these invariants and also find some boundary features that are related to the bulk invariant, right? So indeed, the boundary states of these phases are quite distinct from the ones that one can get within the KTO classification. Okay, so that's again classification for the pair of indices for WLWR. We can actually, under the partitioning of 4 bands here, we can define essentially a valence, submanifold, and conduction. Submanifold where we can, on these pairs of bands, define the non-Abelian connection. So then those will be given as combinations of the Euler connections in the valence and conduction. But you see that they are entangled in the sense that to define these two indices, we actually combine both conduction and valence manifolds. And on a deeper level, we actually related to the optical signatures of these two invariants. But that in principle concludes the section of how to actually calculate the invariants, right? So now I have the bands from the my eigenvalue problem, from solving the Schrödinger equation. Then I can compute an Abelian barrier connection. I can compute all of these connections. I can compute the connections, right? That I originally homotopy.
And you've got an Abelian Chern-Simons structure there.
It's non-Abelian. I'm taking purely non-Abelian part because that's taking off diagonal elements of the non-Abelian barrier connection.
Yeah.
Right. So.
It's an SO2.
No. So yes, in that sense it is.
It's
Yes,
an SO2 that is homomorphic to U1. So it's a Abelian.
Okay.
I mean, reduced is Abelian. Just because it's SO2.
Okay.
It was SO3 or SO4, no?
Yeah, I mean, in principle, we can generalize it right to the case when we have a pattern for arbitrary large. And we only looked at these minimal cases, right? So, yeah, but I agree.
You have generalized, or you can't.
So we can generalize it, right? So of course I can take any number of gaps. The only problem is whether I don't know the homotopy.
You can go to the second Euler number. You can have a.
So that's actually what John Domenico did, taking pi 4 for the higher dimension.
It's purely non-Abelian. I mean, these are like spin connection in momentum space. So in really gravity theory, you have the spin connection for Dirac, let's say theory coupled to curved background. You can think that these mathematical are the equivalent of this object, spin connection, the Euclidean, not in the Lorentzian, but are defined completely in momentum space. So these are the same mathematical structure of spin connection in gravity and Dirac theory.
Okay, so we got the connection out of our block bundle. We calculated all the invariants from the homology perspective. Now let's equip our bundle with Riemannian structure, because it will be actually related to the physical observables. And that picture heavily draws from the following reference by Anne et al. what we will do now that we have the non-Abelian connection is that we will define tangent vectors, and then related to on our Frag manifolds that correspond to the entire block bundle, and then we'll equip it with the inner product structure, which will allow us to define Riemannian. Actually, in principle, it can be Hermitian metric, but it will reduce to the Riemannian metric in our case. Okay, so just a physical insight here. So what we're basically calculating is the transition dipole matrix elements. It will give the connection to optics. Different K points. So what we can do is to take the band or the state MK, connect to the position operator, the state MK. Okay, so writing the eigenstates here, which is formally under periodic boundary conditions defined when n is equal to m, but we'll be only looking at the case when n is different from m. We'll basically keep the non-Abelian boundary connection here. Okay, so. And that in principle we can view as the matrix elements, right, that are entering electron photon coupling. When we couple our topological insulator with the twisted bands in the ways that I described, right? So I can add basically time-dependent electric field, right, as the matrix elements of this perturbation, in which we'll be able to do the perturbation theory. Right, will be precisely given by these matrix elements. Okay, for a block with that K.
Yeah.
Okay, cool. So we have transition dipole matrix elements. Let's define the Hilbert-Schmidt product. First, so now we have matrices A and B. Basically, take the contraction, and trace. Okay, and then what will be our matrices are essentially the tangent vectors. In other words, like manifold, which we will get out of these elements. Okay, so we have for any K point, we have this element, an outer product in bands N and K and M. Okay. Okay, for index I. Actually, the index physically, right, it can run over X, Y, and Z in space. That corresponds to coupling to different polarizations of light. Interesting. Okay.
So why do we need to know the tangent vectors?
Because we define metric with them. So now we will define the metric. So I just, the Hermitian metric, which in my community is called quantum geometric tensor. Metric just follows naturally as a linear product of I and M and M. Okay, which actually has three parts, which is the Riemannian metric, of bands N and M, but there's also the imaginary part, which is the symplectic form. For the PT symmetric systems, this imaginary part will be completely zero because we have completely real eigenvectors. Okay, so you only have the Riemannian metric. So our multigap topological insulators will have under this linear product, structure will have interesting features in this Riemannian metric that we defined based on the connection between two systems. Okay, so we essentially equip now the original bundle here with the Riemannian structure. This turns out to be basically matrix elements squared for the optical transition probabilities between bands and them. Okay, so now that we have the Hermitian metric, we can actually also define a connection. Okay, so and not only connection, we can also define torsion. It's interesting. These have physical manifestations, as I'll show in the very last part.
I mean, at the end, this is just, it's a momentum space Euclidean metric, right? Riemannian. I mean, it's known as quantum metric, but it gives like a classical Riemannian metric that is quantum in the sense it's built by quantum states.
Yes, exactly. So we have the
gravity.
Exactly, right? So the point is that it's true that we have derivatives in like Ki and Kj over our base space,
the quantum state,
but we are taking the quantum states.
Exactly. So behave like a classical Riemannian metric, Euclidean space.
But I mean, in principle, we can define some form of a distance, right? If we take the size of the ones in an M.
Yeah, sure. You can do everything like in the job. It's like gravity, right? Basically.
Exactly. So let's get the connection. So I take still bonds M and N. ATC. Okay. So you can take a covariant derivative of the standard vectors now. And then we can actually also write explicitly in terms of these elements, right? So if I take the here, right, this is nothing more, nothing less than this kind of product. In that case, okay. See, but I also have a gauge derivative even here, so that I can basically get so that's A, C, derivative. I have E, and I'll also keep the gauging to the bare connection matrix. Okay, so I'm defining a gauge derivative of this tangent. Okay, so that's Hermitian metric, and we can define torsion in terms of the Hermitian metric. And again, this is completely real for the space-time inversion. Symmetric topological.
We are basically building Christoffel symbol.
Yes, and now I'll take the
To be precise,
asymmetric.
is that Christoffel symbol?
Sorry.
Christoffel symbol, technically.
Yeah, so we can, in the end of the day, well, okay. So we are defining Christoffel symbols, that's true, but it doesn't need to be the BGB type person.
Oh, sure, it's not. Yeah, technically, yes, yeah.
Okay, so you have.
So it's an affine connection.
Okay. And we can do another symmetrization in the second two indices. And now the interesting thing is that once we write this in terms of the transition depot matrix elements, we can connect it to the probabilities of virtual transitions, essentially, because we have the matrix elements between multiple bands. We also sum over virtual. Okay, so okay. And I'll sum over different bands P and P. Okay. C. Okay. So here essentially we have the matrix elements of this kind squared. In that case, we have an antisymmetrization of going from n to m, but also through t. Okay, that will turn up physically in the response function that we'll be interested in. Okay, so that's the torsion. Okay, so just to summarize where we got so far. So first we defined all the abundance and where the topology is sitting for these multigap topological insulators. From homotopy theory, we got the classification. From cohomology, we got the way to calculate these invariants. Now we get with the Riemannian metric, and now the very final will be to actually connect these Riemannian objects to the physical observables, so that we have the way to probe.
We are talking about condensed matter. Yes.
Exactly. In the end of the day, we want to have some response function that shows us that this topology is there in our material. Okay. So so let me start. And given this connection to the transition matrix elements, it's purely optical responses. What's quite interesting is that, okay, under the PT symmetry, I said like the diagonal elements vanish. The diagonal elements are related to the transport. So in Chern-Simons, for example, when you have the Berry connection A and N, the curvature that you get out of the intraband Berry connection, that is manifested in the Hall drift and in terms of the quantum Hall response. In this case, we have no linear quantum Hall response that requires complex bands that you cannot get from the real bands. But you can get optics from the real bands, and that's what we will discuss now. Being interested in linear and nonlinear responses. So linear order, right? If we write the time-dependent electric field due to the photon field in terms of the frequency domain, we can think about the currents induced and the response function being the optical conductivity. I'm implicitly assuming the Einstein summation convention here, even though I'm only working in the real space. In the spatial domain. Okay, so that's for the linear currents, and then we can also consider nonlinear ones. At second order, we'll have a linear conductivity tensor. Essentially, have a combination of two optical fields, so the frequencies 1 and 2. So what to be interested in is actually, in that case, the response. Sorry.
So that can't be. You use the same symbol, except you didn't do it.
I added one more units.
No,
Sorry, for which one?
left one.
Ah, yes. So that's not linear. Sorry. So that's the linear current. That's the nonlinear. Right. So omega will be given basically by the combination of these two frequencies, right? So we are driving a system with two optical fields, and then essentially the energy conservation will pose a constraint, right, of what frequencies we can get in the response, the photons. In particular, if you take single frequency and consider a linear process where you have these out of phase, right, you can consider omega and minus omega components, and then this would basically sum to 0, and we can get DC current, right? So this is non-oscillatory now, out of nonlinear coupling to light. Okay, and that's basically photovoltaic effect, right? We nonlinear coupled our material to light, we got the DC response, and there are actually two contributions that are called shift and injection here. Shift arises from positional shifts on moving between the original band and the excited band as the electron is changing the position. In the case of the injection, which we will not be interested in, we essentially have a different velocity in two different bands. So we do an excitation, but in principle, given the dispersion of different bands, the electron can have a different velocity in one band compared to another. Okay, but we'll be interested in this geometric shift part, which can be decomposed in terms of part that comes to linear polarized light and the circular one. So this is basically the real, this is imaginary part of the tensor. Okay. Okay.
Basically, just to repeat, you have a piece of material and you are sending on it an electric, time-dependent electric field. And you want to study some response of the material.
Yeah.
And show that the differential geometry is behind this response.
Exactly. So I want to show that
the emergent geometry gives you the physical response of this of this piece of material in presence of electric field.
Precisely, right? So I will write these correlators right now in terms of the geometric objects that I introduced,
Sorry.
which will be inherited. Okay, so by doing perturbation theory in the electric dipole Hamiltonian that I wrote down, I state the final answer, which is also in symmetry physics paper that I mentioned. The final answer is, for the linear case, we basically have a sum for all of the states responding around zone. Okay, so make a phase space integral here. Given the occupation of the states, again, I'm talking about electrons, so they will satisfy Fermi statistics. The occupation numbers, and in particular, I'll be working in zero temperature limits, but I have a different occupation between the bands from which we are exciting, which I call small m, and the bands that is unoccupied and which we are exciting our electron, which is band m. There's, of course, energy conservation condition. Right, so for n k, you have an energy difference, right, between m and band. And finally, the geometry. So we have the multiband metric, which I defined in terms of the Non-Abelian wave connection equivalence there. And as promised, these actually reflect the polarization, right? If I use the x polarized field, I'm making this component x, this metric that is sitting there in the connection, so that's sitting there in the Bloch bundle of the topological insulator, can be essentially to the response. So now, interestingly, what turns out is that whenever you have Euler bands, because of the positive semi-definiteness of the quantum geometric tensor, you get the bounds on the curvature that I defined previously. So in particular, if you take the bounds with the Euler class, okay, so and you consider the other bounds, and you sum these matrix elements for x and for y. You get an inequality that holds loci in the K space. And then, of course, as you sum over all of the states in the Brillouin zone, you can basically show, right, on integrating this, that there's a bound given by the Euler class. So what would be useful, would be to write it in the integral form. So this is basically what I will define as trace g chi, okay, which are these particular metric Riemannian metric elements, okay. And now, if we do an integral over the Riemann zone, this will turn out to be lower bounded by the Euler class of these two bands. Okay, so what is the physics of this result? The physics of this result is that if the Euler bands are in your topological insulator, there is a constraint from the topology, or actually the minimal bound, on how much I would say deformed the Riemannian metric is over the Bloch bundle, and these metric elements enter the optical response. So indeed, we actually get a set of optical bounds. Okay. So for which I will my so-called optical weights by integrating the real part of optical conductivity. Again, like, okay, formally this is just the real part. There can be also imaginary part that's related to the symplectic form, but symplectic form is vanishing in this symmetry system. Okay, so if we integrate this real part of conductivity over frequencies of the photons, okay. Optical weight. And indeed, right, if we divide by omega here, set the zero temperature limit over there, integrate over all of the frequencies, we get the bounds that are purely geometric, right? So I'm just getting rid of everything else other than the metric by defining the right optical quantity, this optical weight. And then indeed, if you combine the optical weights of the system at the zero temperature limit when the bands or other bands are occupied or not potential, so I'm considering a case when I have a pair of Euler bands that might be separated from the other bands by some gaps 1 and gaps 2 in a physical system, and basically investigating the possible transition rates to the Euler bands, and in that, if I set the terminal here, or from all of the from these bands also to the higher bands if I was to set the different right? So that's what I mean by occupied and unoccupied case, right? So to basically get this kind of bound. Okay. For a combination of two linearized polarizations. Right. This indeed the mix of the activity will be lower bounded by the Euler class. And the comment is the following. So far, we induced non-trivial topology in our Bloch bundle. That gave interesting geometry that is actually lower bound, topologically lower bound. Okay, and that's the statement of this lower bound. What is interesting now is that we can actually do an inequality, right? If we have the gap here, well, the minimal photon frequency, because the excitation will be actually given by this gap. So what we can do is to consider the following sum. Right, so I'm basically trying to set another bound, given what excitations are possible with all the photon frequencies. But that is actually the integral of the real part of the optical conductivity, which defines the F-sum rule. So that's actually given by the size of the gap. The result of response theory. So if we do this type of inequality, right, on setting here the band gap to be G1 and G2, we can actually get a constraint on the size of the band gaps below and above, as long as we as the sum rules are satisfied, right? So that implicitly also assumes that the Hamiltonians that we are considering that gain this topology are local. But in principle, one can get out of the Euler class a bound of the harmonic mean of these two gaps from this inequality on applying the other one. Sorry. That essentially means that if the Euler class is vanishing, there is no bound whatsoever. But if this topology is there, as long as the Hamiltonian was local and the sum is fault, there is actually a bound on also the gap size. And again, that equals locality, because in principle, I could have taken whatever energies and whatever bands in a flattened limit and so on, but locality might be gone, right? But if I actually have a local Hamiltonian, this is one manifestation, so that's a bound. So, okay, that's geometric bound. Now let's consider actually something to be quantized, which is optical conductivity in the case of an Euler node of Quaternion class. So this is the bulk Euler class over data everyone's own, giving a bound. Now we'll comment on the manifestations of the Quach Euler class. So I already promised, right, that we can think about the vorticity of the non-Abelian connection or of the Euler connection around the Euler node. And within the continuum models basically show that independently of the dispersion of the bands, as long as the vortex of the non-Abelian connection is there, we can essentially get a universal optical conductivity on using the expression that I wrote down there, basically. Is given by the Euler class. What it amounts to is essentially found in the form of the metric, which reflects the singularity, the vortex of the Euler connection. And now, if we think about being very close to the node, right? So that's energy. Next, why we have the momentum space. We basically get from the singularity in the metric, we get the quantized optical conductivity. So let me do this here. And the conclusion essentially is that whenever we have multigap topologies associated with the Euler class, we not only get the bounds from the Euler class on the optical observables, but we also can get the quantizations for the partial. Okay. So now the very final thing, let's readdress the Hopf indices and the isotopic winding indices. So you look at the circular part of the shift photoconductivity here. So first of all, we can connect it to torsion. The way we could connect the linear optical conductivity to the metric was useful to probing the Euler class, but now for torsion, what we get is that if we take an antisymmetrization of the circular part of the shift photoconductivity, you do again a spectral integral. First of all, that is a sum rule that is given by this multiband torsion. Now we are looking at the nonlinear coupling, right? So we actually have higher power the charge. Okay, so so now we are talking about three-dimensional systems rather than two-dimensional ones. Okay. we're taking complete anti-symmetrization of the torsion. First of all, it gives us, just using the definition of the shift photoconductivity, which I will just write. So I wrote down the optical conductivity for the linear case. Now for the nonlinear one, again, we can recast it in terms of the, not in terms of the metric, but in terms of higher derivatives, in terms of the Hermitian connection. So let me just quickly write that, just follow the conventions of the Nature Physics paper I mentioned, ABC, that we can look at as integral of the okay, again we have so all the particles, set up the occupations. Energy conservation, and now the geometric part being the Hermitian connection. Okay, this is indifferent. This is so current is actually in A when we couple B and C. So if we sum over all of the imaginary parts and anti-symmetrize, indeed we will end up with the torsion, right? Which is not surprising because the anti-symmetrization of the connection should give us the torsion. But then the question is, okay, what happens next? So what happens next is that we can actually show that these sums of the torsion reduce these Chern-Simons forms that I was writing down in the first part. So we can show that these used to which U where or for the Hopf case or a single like manifold index or combinations, actually a sum of them or the other flag indices as inequality numbers. So what we get is essentially a quantization condition on integrating over all of the momentum states that we have over the ground zone. In terms of the sum of these two indices for the 4-band case, so that's the 4-band, or in terms of a single index. In the 3-band case. To summarize, in that case, we get essentially a sum rule or a spectral integral of the circular part of the shift photoconductivities that is topologically quantized by these Chern-Simons forms that are actually on the geometric side equivalent to the anti-symmetrization of the torsion tensor. And again, this was related to the virtual transitions, right? Nonlinear response, right? Where we couple to first photon, go from state N to some state P, then we can get to the state M, to the final state, by coupling to the second photon. Okay? So we get a nonlinear sum rule here, but it gives a topologically quantized circular shift response. And that we reported in physical review letters. Last year.
Remember all the numbers, right?
Yes. That is definitely the most precise part of the talk. Right. So now there's a very final flavor. Let me just mention one important thing. So the nonlinear responses for even order, right? So for example, coupling 2-photon coupling, 4-photon coupling, they're vanishing under the inversion symmetry, given how the photoconductivity tensor transforms. Now, for PT symmetry, you have two different cases, right? So you can have PT, which comes from having both P and T, but we can also have the case where P and T are broken. So actually, for this invariant, we showed that this necessitates the breaking of both. So we are fine with this response. Actually, the case of these two winding numbers is a bit more intricate, because there we can have both P and T while keeping the PT, but then actually the response vanishes, because whenever we have P and T, WL plus WR is vanishing. Whereas whenever we have P and T broken, then these indices are not equal and opposite to each other. But that is consistent with the inversion symmetry. For the four-band, right, we can define the inversion symmetry Hamiltonian, but then it will have no net response, right? Which is fine. Right. So that hasn't been measured, by the way.
Yeah, exactly.
So far.
There are experiments. Experiments, no?
Sorry?
This has been tested. I mean, the measurement of the photoconductivity has been done already experimentally.
So okay. So we need to be very careful here. So this hasn't been measured, and in principle, when you do this anti-symmetrization with quantization, right, we need to have all of the x and y and z indices, right? So the point is that, of course, we are doing technically an integral, right, in kx, ky, kz. So then we, of course, need the derivatives in x and y and z here. So one would need to look at the response, right, when we couple circular slides in y and z, and look at the response in x, right? Actually, some classes of materials that are precisely consistent with these symmetries, so we have PT symmetry, but P and T are broken, which are antiferromagnets in 3D. They are known to have quite enhanced responses in, for example, in the case when one has two y indices here, right? So it's known that the antiferromagnets in 3 spatial dimensions, especially the ones that realize theta vacua that are related to Chern-Simons forms, can support photoconductivities for the other combinations, right? Which might be related in principle to torsion, right, for the circular polarization. When we have here, let's say x, and then here x and y, right? But the x, y, z, this has never been measured, and well, hopefully, at least approximately this quantization would be true. Because here, formally, what we do is that we look at the low energy subspace, right, that can be characterized with these topological invariants, as long as we don't mix with the other bands, right? Because that allows to isolate this effective Bloch Hamiltonian, and then we are thinking about, right, excitations here and getting photovoltaic response out of these excitations. Again, the necessity of additional bands is there because we need to get the multiband torsion out of that. Whether this will be measured, we will see, but let's hope. But at least in terms of symmetries, everything is consistent. And on that flavor, let's move on. Thank you so much.
Okay. Thank you. Question?
I just want to say something. It's not a question. Sorry, Wojciech. Just wanted to advertise this. Marek is going to give a talk on black hole mirrors and other recent work of Neil Turok tomorrow at 2:30. And we haven't had a notice of that yet, but because I have to go. It's a very good talk. Thank you so much.
Thanks. No questions? Nobody survived? No. Well, I have a question. Okay, I enable that because in the Euler class, let's talk about Euler. So, well, you showed indeed there is a bound between the Euler and the quantum metric, right? This is, but if I think in terms of the Gauss-Bonnet, no, because I mean the Euler I can write the Gauss-Bonnet. So I can build also. I have the quantum metric. I write the Christoffel symbol. I write my Riemann, Ricci, and the Ricci scalar, and put Gauss-Bonnet into dimension. So is there, I mean, can you map the expression that you have with Euler there with connection? We just writing in terms of the quantum metric, but not like a trace. I mean, it has ever been done this? I never checked this.
So it's not about connecting to Riemannian curvature itself, but so okay. One thing is the curvature is actually related to nonlinear responses, which is for transport.
No, for transport is fine. Yeah.
For these. In the paper by Anne, it was shown that the Riemannian curvature integrated to the third order photovoltaic qualified.
Yeah.
But in principle, then it gives a difference of the Chern numbers, and then the Chern numbers are vanishing in the case of the real bundle. Okay, so it could be right that there are some interesting higher order responses. For example, to circular characterise like that could pick something of a similar form, but not exactly the Riemann curvature, because it basically reduces to the very curvature. Exactly, which is vanishing, right? Because all the symplectic forms.
You don't have a symplectic structure.
It's completely gone. Yeah, because of the spacetime inversion. So, but yes, perhaps there are some still further signatures at the higher orders that remains to be investigated.
Okay. Yes, there are no questions. Other questions? So again, let's thank the speaker. I also stop recording. The stop recording is not stopping.